Good morning, everybody. I'm going to finish off the year by doing a short little unit on electrochemistry. I think it's some fun chemistry. I think it's some interesting chemistry, and it's a way also to tie in redox and to wrap that up, and also to wrap up the year. First of all, I want to congratulate all those of you who took the national exam. While it was a daunting challenge, I really do appreciate and applaud all of your efforts leading up to it, and regardless of the outcome, I just want to let you know how proud I am of you for taking on that task. To wrap this year, what I'm planning on doing in the next couple weeks is each week I plan on doing like two little video lectures on electrochemistry, and then to have you guys do like a small little short homework problem that follows. Okay? So this lecture today is just going to focus on what a Voltaic cell is, how it works, how it operates, and how we can predict the voltage that combination will produce. And then I will have for tomorrow, I'm already going to upload it today, if you can do it today if you want, but I'll have a homework for you just to complete and answer the questions. It shouldn't take more than probably 5 to 10 minutes, and then submit it on Canvas, and that will be one half of this week's work. And then I'll do the same thing on Wednesday and Thursday this week. And we'll do two of these each week, each of the next 2 weeks, and that'll wrap up the year. As I've been told, the end of next week will be the last time that we really have to submit any or have you guys do any type of work or submission of any kind. Okay? All right, so let's talk about so a voltaic cell is an electrochemical cell, and therefore there is electricity produced. And a voltaic cell is a spontaneous cell. For those of you that did go through the lecture on the unit with spontaneity, just before, actually right after the pandemic hit, where we were no longer going to school, a spontaneous cell is one that naturally occurs. So in a voltaic cell, the combination of the two electrodes, the cathode and anode, have a flow of electricity. And a flow of electrical current is nothing more than a flow of electrons. When we have a flow of electrons, that is what we call current. And that current can be used to power a lot of our devices with electricity. Batteries, great application of this. So it's a cell that naturally occurs once we create a full circuit. And we'll show that in the picture down below. Now, to do that, we have to revisit redox reactions. Oxidation, reduction, half-cell reactions that we combine to create one overall equation. Up above, we see the normal iron reaction that we did at length throughout the whole year. And in this iron reaction, the iron goes from +2 to +3. Again, those are not only its charge ion state, but also its oxidation number. And you can see that the iron is becoming more positive. If it's becoming more positive, it is losing electrons, and therefore this is an example of an oxidation half reaction. The permanganate, specifically the manganese in the permanganate, has a oxidation number of +7, if you'll remember. And then it becomes +2. It has become more negative. It has gained electrons, and therefore is the reduction half reaction. And therefore, electricity is going to flow. The one that loses electrons, the iron, which is losing electrons, producing electrons, that will flow into the manganese, and that is going to give the manganese reaction electrons to complete the circuit. And that flow of electrons from the iron to the manganese is going to create current, electricity. And that flow of a current will continue indefinitely. Until eventually something takes place. Now, electrochemical cell potentials is a lot like if you think of a waterfall. In a waterfall, we have water that is at a high potential energy, specifically a high gravitational potential energy. When we lift things up above the ground, they get more and more potential energy, much like a roller coaster. When that chain pulls a roller coaster all the way up to the peak of the first hill, we are giving that roller coaster and its occupants gravitational potential energy. When the roller coaster flows, or in this case water flows over top of the higher located height position and flows down to a lower, it flows from a higher potential to a lower potential. And that water is a natural progression, just like the roller coaster naturally coming over the hill. And that's going to naturally flow from high to low. Well, the same thing happens in a battery. The battery has two compartments that are separated together. And electrical current, just like a waterfall, will flow from a high potential to a low. But as that high potential flows into the low, the high potential starts to decrease while the lower potential begins to increase. Eventually, the two potentials reach the place where they are equal to each other. And now electrons will no longer flow from one to the other because there is no longer a differential in potential. And so this cell will continue to operate until both half cells, half reactions, will reach the same electrical potential. And then the cell will no longer operate. We have a dead battery. And that's what electrochemical cells are. Batteries will operate, but again, there's a limit to how long they'll operate. And eventually what will happen is the battery will go dead once those cell potentials are no longer have a differential. Okay. Now, if this is a rechargeable battery, we can then hook it up to electrical current, which will flip the polarity, and now the potentials will again change to high to low. We'll recharge the battery, and then we can go ahead and plug it into our device and allow it to operate again. Now, there is a limit to how many times we can recharge these things. And you'll notice that over time in your cell phones, initially it holds a lot better charge and it will recharge and it'll do a better job. But over time, as you keep recharging it back and forth and flipping the polarity, there is eventually a limit to where eventually the battery starts to not hold its charge as effectively and where you again might have to replace the battery. So again, there's a limit to how many times you can do this. But again, that's what's happening. Current flows from high to low, just like water flows from high to low heights. It's a spontaneous natural progression. And electricity will always flow from the oxidation half potential to the reduction half potential. Okay. Now, in this reaction, iron, you'll notice that it changes oxidation number by 1, but we magnify it by 5 so that the reaction is balanced. In this chemical reaction, okay, and the manganese goes from +7 to +2, or a value of 5, we get 5 electrons. So when we have 1 mole of this reaction, when 1 mole of this reaction takes place, it will produce 5 moles of electrons. Okay, and so that's how much electrical current could be created from this combination of this iron and permanganate reaction. It can produce electrical current. Okay, now a diagram of a voltaic cell I've shown below. What I have here is 2 beakers. And we're looking here at the voltaic cell that occurs between copper and zinc. Now, what are the components that make up a voltaic cell? First of all, we have to have individual compartments that are separated. And in the compartment, we are going to put a solution that contains both the ion and the solid state. You'll notice down below at very far, I have what's called the reduction potential. In electrochemistry, you're always going to be given the potential of each of these half reactions, how many electrons they produce per mole, and they're always written as a reduction, and therefore the electrons are on the reactant side. So all of these are reduction potentials. Okay, so this is how much electrical current can be produced from this 1/2 reaction. For copper, going from copper +2 to copper, it can produce 0.34 volts. Zinc can produce 0.76 volts. Therefore, zinc has got a higher reduction potential because it has a higher voltage assigned to it, okay, with its electrical current. Okay, now, therefore, in each half reaction, we must have both aqueous copper ions and copper solid. So in the half cell that contains copper, we will have copper ions. So we'll create a solution that contains copper 2 ions. And remember, copper 2 ions have got a blue color. So this cell will have a blue color. Zinc ions are colorless. Right? Along with having the aqueous zinc and copper ions in each of the half cells, we have to have a solid piece of copper metal. And that solid piece of copper metal is called an electrode. An electrode is a solid material that will allow the electrical current to flow into the compartment. And now inside this compartment we have both solid state copper and aqueous copper ions. And that's where the half reaction will take place. We have both requirements, both the solid state copper and the aqueous copper ions to have this half reaction. The same thing is true about the zinc. The zinc electrode will be made out of zinc metal, and there are the two half compartments. Now, the concentration of the ions are both 1 molar because 1 molar is considered standard state. Just like 25 degrees Celsius is standard state for thermodynamics, 1 molar solution is required for copper and the zinc, so that we have a standard cell. These reduction potentials that we have down below are when we have a standard. And we can tell it's standard because that little 0 up at the upper right-hand corner. So this is when we have 1 molar copper ions and zinc ion solutions. Okay? So therefore we have to make sure that if I want this voltage to measure out to what we predict it'll be, we have to use standard aqueous solutions. There are a couple other diagrams to fill in with this voltaic cell. The next is we've got to connect the two cells. And to make that connection, we'll use a piece of wire with alligator clips. And that wire will be connected to what's called a voltmeter. And that voltmeter will allow us to measure how much current will be produced. Okay? Now, so that voltmeter, usually labeled with a V, will tell us what this voltage is as this electrical current will operate. The last thing that will complete the circuit, right now we don't have a full circuit, we don't have a full loop, is we have something what's called a salt bridge. And the salt bridge is usually in a U-shaped channel which contains a salt. In this case, usually it's sodium chloride. And the sodium chloride is ions that will naturally flow into these compartments as these cells operate, and I'll talk about that in a second as to how they will flow and how this will migrate and move. Okay, so this is a standard picture of what a voltaic cell will look like. We've got a voltmeter, a wire that makes the connection to the two electrodes. We have both the solid state material and the aqueous ions, that same material, in connection. And then we have a salt bridge that will complete the full circle. So we have a full loop that is created, much like in, for those of you that had physics, with electricity as well. We have a complete circuit that is produced from this. Okay? Now, the next thing to do is to label each of the compartments. Which part of this battery is the anode, which one is the cathode? You'll see above, the anode is where oxidation occurs, the cathode is where reduction occurs. Well, we can't have both reactions undergo reduction potentials. They both can't be having gaining electrons. One has to gain, one has to lose in order to have a redox reaction. How do we tell? The reduction potentials. The reduction potential that is the largest, the most positive, will stay reduction. So what we'll do is we'll flip the copper reaction, will be flipped, and it will become a oxidation potential. And when it flips, what happens to its voltage? Well, just like enthalpy, when you have an exothermic reaction and you flip it, becomes endothermic. Same thing here. When you have a positive cell potential one way, when you flip it, it becomes negative. So it becomes negative 0.34 volts. The zinc reaction will stay because it is the higher of the two. So its reduction potential stays at positive 0.76 volts. Okay? When we add up these two reactions, we get the overall chemical reaction that takes place. Copper, because both of them have two electrons, their electrons balance. If they don't balance, then we have to multiply each of these half reactions by a number to get the electrons to be the same on both sides. If you remember back to redox balancing. So copper solid plus zinc ions will produce copper ions and zinc. And the voltage of this cell will now be the addition, just like enthalpy, we treat E just like enthalpy, will be the addition of these two values. So negative 0.34 plus 7.76 volts will add to a voltage of this cell operating at 0.42 volts. So my voltmeter up here would register, once the connection is complete, it would read 0.42 volts. Whenever we have a voltaic cell will always have a cell potential that is positive. It has a positive voltage, and that is the voltage of this, in essence, this battery. We would produce 0.42 volts of electrical current with this zinc and copper reactions. Okay? Now, because the copper is flipped, it is undergoing oxidation. So the copper side, because it's undergoing oxidation, it is going to be the anode. Oxidation is where the anode. So the copper side would be the anode of the battery. The zinc has got reduction undergoing, so it is the cathode. So now, because we know whichever reduction potential is the highest will be the cathode of the battery. The other half reaction will be flipped, and that will then be the anode of the battery. As I said before, because the anode oxidation is producing electrons, electrical current will always flow from the anode to the cathode. Oxidation flows into reduction. So the electrical current of this wire, the flow of electrical current will flow from the anode, the copper reaction, into the zinc reaction. Oftentimes on the national exam, okay, you would ask to draw on the diagram which way the electrical current will flow. It'll flow from the copper to the zinc or from the anode to the cathode. Easy way to remember that, much like Q and K, okay, we would use alphabetical order. It always flows from anode to cathode, A to C, okay, anode to cathode. All right, so as this cell reacts, we're going to produce 0.42 volts. Now, if I look at the copper side, in the copper reaction, the copper solid is becoming copper ions. Therefore, the electrode, the solid state copper material, is being converted. So the solid copper is going into the solution, producing more and more copper ions as this cell operates. Well, that's going to build up positive ions. That's not a good thing, because as more and more positive ions build up, we're going to have a charge differential that develops. So what happens is two things happen here. First of all, the electrode, if I were to operate the cell for a while, if I were to mass the electrode before the cell is started and after the cell operates for a time period, I'm going to notice that the electrode is going to lose mass. Well, that should make sense, because the solid copper that makes up the electrode, as this reaction continues on, that solid state copper will go into the solution producing copper ions. It has to come from somewhere. It comes from the electrode. So the copper electrode is going to be smaller and smaller and smaller and lose more and more mass as it goes into the solution. Also, because more and more positive ions are building up, in order for this cell to keep measuring and keep undergoing its 0.24 volts, for it to keep operating, the concentration inside the cells must stay neutral. Well, if I'm building up positive charges, I've got to put in something negative, and that's the purpose of the salt bridge. The chloride ions in the salt migrate into the anode, okay? They flow into the anode to balance out the positive buildup of the positive 2 charge on the copper. So the purpose of the salt bridge is to put into ions into the cell compartments to keep the concentration of the cells, the sum of the particles in the cell itself, the solution, to be 0. And therefore, negative charges have to flow in to balance out the increase of the positive side. The opposite true is in the cathode. In the cathode, the zinc is becoming zinc ions. Excuse me, my bad. My fault. The zinc ions are becoming zinc metal. We have reduction going on. So the zinc ions, the positive zinc ions, are becoming solid zinc. And therefore, the ions in the solution are adhering to the electrode. The zinc ions, as the electrons flow into here, the positive zinc ions adhere to the surface, becoming solid state zinc. So therefore, the solution is losing positive ions. So what has to come into the solution? The positive sodium ions have to flow into the cathode side to replace the lost zinc ions that are now being deposited, plated. This electrode, you're going to see plating take place. It's going to gain mass. So the cathode will have an increase in mass because the zinc ions in the solution are becoming solid state and deposited on the surface of the electrode. And that's going to cause the electrode to increase in mass. The copper is going to lose mass. Since zinc ions are being pulled out of the solution, other positive ions must replace it so that the concentration, the total sum of charge in the solution stays at zero. And therefore, the positive ions go into the cathode. What's one way to remember that? Cathode, the sodium ions, positive ions are cations. So the cations flow into the cathode, and the anions of the salt bridge go into the anode. So once you are able to label which half reaction is which, you should then be able to know, okay, in the anode, the anion of the salt goes into that, okay, to equalize the charge. The cations go into the cathode. Electrical current flows from the anion to the anode to the cathode. And lastly, the electrode, that is the anion side, will lose mass while the cathode side will gain mass. So once you identify and label the anode and cathode, a lot of those standard questions will come true. So when we're done here now, we know which way the current will flow. We'll know how much current flows, in this case 0.42 volts. We'll know which side is the anode, side is the cathode. Okay, we'll know what the purpose of the salt bridge is, to keep the sum of charge in both solutions being neutral. And we also know that the electrode, one will gain mass and one will lose mass as the cell operates. Okay, and this is the common diagram of a voltaic cell. Okay, and a voltaic cell is a spontaneous cell that naturally occurs where electrical current will always flow from the oxidation half reaction, the anode, to the reduction cathode, and that flow of current is called electricity. And this is what batteries are. Okay, so for your homework tomorrow, all I had you do today is just listen to this video. So for your homework the reason why that is because if I take the potentials and I both increase them by 2, the differential is still the same even though I multiplied. I multiplied both sides by 2. So the differential, the difference in the gap between high and low, has not changed because I've increased both of them by a factor of 2. And therefore, cell potentials do not change when you make. I've uploaded a diagram, and I'd like you to complete the diagram in here, putting in the solutions, putting in the electrodes, putting in the salt bridge, labeling each of these, connecting it with a wire to a voltmeter, labeling all these parts, identify who is who, and answering these questions, and then determining what the overall reaction is between magnesium and silver, and also identifying which way the current will flow, just to kind of recoup all of the information that I gave you. Once this is all completed and labeled and you answer all of the questions down below, take a picture of this and upload it into Canvas, and you'll have completed 1/2 of already this week's material. Okay. One last thing that I forgot to identify. You'll notice up here with the magnesium and the silver, one is with 2 electrons, one is with 1. So you will have to multiply the silver reaction to get the electrons to balance. Well, I forgot to mention what happens to the reduction potential if I magnify a reaction by a coefficient. The answer is nothing. Both of these voltages will stay the same size. The only thing is one of them you will flip. So one of them you'll flip the sign of it. But if I multiply a reaction by 2, like the silver reaction, I do not multiply the voltage by 2. And why is by them? Okay? So when you do the voltages here, all you've got to know is that one of them you will flip, okay? And then you'll add them together. But for cell potentials, you never change what their voltages are because of the fact that you're magnifying both sides by a common coefficient. Okay, thanks again for listening. I apologize for the length again. A lot of parts to this, but the next lecture this week will be much, much shorter, and then the homework problem should go very quick. But this homework problem should not take more than, again, 5 minutes for you to do if you've listened to the video. Take the picture, submit it, and you're doing exactly what you need to receive credit for this class. Again, thanks for your time. I appreciate that. If you have any questions, again, just send me an email. Thanks so much for listening. Goodbye.